Hello everyone, I am Jimao Chen, a master student from the Department of Electrical Engineering at National Taiwan University. Today I will be presenting my research on FPGA controlled high-power driving design for high-intensity focused ultrasound applications. My research is conducted under the guidance of Professor Haoli Liu. This presentation will follow the outline structure. I will begin with an introduction, where I will provide an overview of focused ultrasound systems and discuss the motivation behind our research. Then, I will delve into the methodology and theory we employed. Finally, I will present the results and outline our future work. Focused ultrasound is a non-invasive therapeutic technique widely used in applications such as thermal lasering, blood-brain barrier opening, and neuromodulation in the central nervous system. It involves exposing focused ultrasound waves through skull bone onto the target brain region, cause rapid and effects such as thermal lasering, drug delivery, and epilepsy treatment. A FAST system can be divided into four main components: a computer interface, a signal generator, and driving unit, and an impedance matching unit. The system is connected to a concave ultrasound transducer for focusing. While single-channel FAST systems are prevalent in the market, recent research suggests that multi-channel phase control offers enhanced flexibility by allowing control of the focal point and depth. However, as the number of a channel increases, system volume and complexity become significant challenges. And to improve the efficiency of phase control, the use of microcontroller, MCUs, and field programmable gate array, FPGA, have been proposed. These devices enable precise and real-time signal and phase control. The driving unit of the system is another significant focus of research. Most studies use nonlinear amplifiers such as Class D and Class E, as known as the switched excitation amplifiers, due to their fast speed and high conversion efficiency. However, these amplifiers have limitations in focused ultrasound application. Switched excitation amplifiers rely on PWM modulation of the input signal, resulting in output signals composed of numerous square waves. This causes higher order harmonic in the output signal, leading to side lobes in the acoustic field, which in turn affect the energy and position of the therapy. Furthermore, over time, the surface of the piezoelectric ceramic in the transducer may be damaged, causing a shift in a central frequency. The output stage of the switch excitation amplifier forms a resonant circuit with inductance and capacitance, allowing only a very narrow range of frequency to pass. If the central frequency shifts, the output inductance and capacitance must be readjusted, which becomes more complicated and inefficient when applied to the multi-channel phased ultrasound system. This is the Class D driving circuit, and this is Class DE. Their output waveform like this and like this. We can see that their third harmonic to the fundamental from the Class D output waveform is about 20% to as low the 5%. And if we do not do any adjustment, the switch excitations results will very different to the linear amplifier, like this and this. Our motivation is the multi-channel fast systems require a high frequency and higher precision control center to meet phase control needs and enhance system convenience. For fast applications, it is optimal for the ultrasound transducer to receive an electro signal without high order harmonics to achieve the best focusing effects. Therefore, fast system output should be as close to perfect sine wave as possible. Thus, this study presents a designed 4-channel driving system for fast therapy, comprising a field program gate array FPGA, high-speed digital-to-analog converters DAC, and a push-pull power amplifier-based driving circuit without higher-order harmonic. Additionally, considering the potential central frequency shift of the piezoelectric ceramic ultrasonic transducer with prolonged usage, the system features a chirp mode to assist user in rapidly identifying the central frequency of the ultrasound transducer. And here is our system architecture. Our architecture, the operational principle of the system is as follows. First, a user-friendly GUI interface developed in the C# allows a user to input signal parameters. The input data is processed using algorithms and transmitted to FPGA through the USB 3 module. Second, within the FPGA digital data is stored in register and RAM. An internal finite state machine controls the signal output to the DAC, which converts the digital data into high precision analog signals and have the phase delay with each channel. Third, push-pull driving circuits amplify the analog circuits, and simple impedance matching components efficiently transfer energy to a 4-channel ball-shaped ultrasonic transducer, resulting in a generation of acoustic pressure. The signal generation stage is structured as shown in the diagram. User can select either burst mode or the chirp mode through the graphic user interface GUI that we have designed. In burst mode, a standard signal for focused ultrasound therapy can be configured with parameters including peak pressure, frequency, burst period, burst length, and the total duration. In a chirp mode, users have the capability to quickly identify the central frequency of the ultrasound probe. Following mode selection, users can input waveform parameters. These parameters are processed to digital data through our proprietary algorithm and then transmit to USB 3 module. From there, the data is further passed into the FPGA for storage in internal registers and RAM. Within the FPGA, our custom-designed hardware algorithm takes charge of controlling the digital data feed to 4 DACs. These DACs perform the essential function of converting the received digital data into analog signals, thus achieving signal generation. Our driving circuit block diagram is as below. There have 3 components: a non-inverting LPA, a voltage amplifier, and current amplifier. First, the non-inverting LPA has the first time to amplify the input signal, and the voltage amplification stage comprised a combination of common emitter, common base, and common collector amplifiers. The common base amplifier enhances frequency response by minimizing the impact of parasitic capacitance in the BJT. The common collector amplifier maximizes voltage amplification. In the signal component stage, the amplified positive health cycle and negative health cycle are coupled. Low power BJTs are used to prevent DC signals from flowing into the subsequent stage. It provides a stable zero bias voltage source for the subsequent stage of current amplification. In the current amplification stage, a 2-stage amplification approach is employed. Each stage outlines parallel connected power BJT common emitter amplifiers to perform current amplification, providing larger current to the transducer. In our matching unit, we have incorporated a self-impedance transformer connected in parallel with the transducer. Our transducer is using the piezoelectric ceramics, which can be examined from both a mechanical and electrical response perspective. In the figure, Fs represents the resonance frequency, while Fp represents the anti-resonance frequency. On the right side, we have the equivalent circuits of an ultrasound transducer. The transducer exhibits maximum vibration at the resonant frequency. During this time, components L1 and C1 in the equivalent circuit create resonance, effectively become a resistor R1 and in parallel with the capacitive impedance of C. Therefore, by adjusting the impedance to match the output impedance of the driving circuits and setting the phase angle to the 0 degrees, we can achieve the desired matching. In our matching units, we have incorporated a self-impedance transformer connects in parallel with the transducer. And this configuration serves to reduce the impedance on the transducer side and adjust the phase angle to the 0 degrees, effectively bring the transducer closer to a pure resistive load. And here is our system output. In burst mode, with a central frequency of transducer, our transducer's central frequency is 500 kHz. As an example, the maximum voltage peak to peak can reach to 120, with a constant 90-degree phase difference between bursts. In chirp mode, ranging from 300 kHz to 700 kHz, it can be observed that the voltage peak to peak remains nearly constant despite the varying frequencies. And after performing a fast Fourier transform on the output waveform, it can be observed that the third harmonic, 1.5 MHz, constitute only 2.4% of the fundamental frequency's energy. This demonstrates that the system effectively concentrates energy at the central frequency of the ultrasonic transducer. In the sound field, we simulate the acoustic pressure distribution of the ultrasound in water using MATLAB. Mode 0 corresponds to 4 transducers with phase coherence, and Mode 1 represents a configuration with each channel having a phase difference of 90. In burst mode 0, we obtain the acoustic pressure curve shown in the figure, corresponding to the different input signal magnitude. The maximum focal point acoustic pressure can reach up to 3 megapascal. Here's our conclusion. The user interface enables real-time visualization and operation with adjustable mode and parameters. The system generates a 3 megapascal peak pressure output and mitigates high-order harmonic issues caused by capacitance and inductance. These developments provide possibility in designing a portable multiple-channel transcranial fast system for future brain therapy. In the future, we plan to apply this system to animal experiments to assess its actual therapeutic efficacy. Thanks for listening.